Hello, this is Jason Kendall, and welcome to the next of my introductory astronomy lectures. Today we're going to be finishing off our exploding, dying stars and the lives and deaths of stars with supernova remnants, some of the most beautiful objects in the sky to go look for with a telescope and to look for with telescopes that aren't your eyes, meaning something up in orbit or with Hubble Space Telescope or in X-rays or infrared or gamma rays or so forth, because supernova remnants emit huge amounts of light. That is a very, very strange source of light, and unlike stars. So these are the bits from the dead stars that we saw last time when we looked at supernovae. All right, so let's review again what supernovae are. Supernovae come from extraordinarily large stars, stars more massive than, say, 5 to 8, roughly 10 times the mass of the Sun, which are the top 3 rows, or more specifically, the second and third row from the top. And we see that, there's 2 types of stars, blue supergiants that become type 2 supernovae and become black holes, or it becomes a supergiant, a blue supergiant that becomes a type 2 supernova and forms a neutron star. So these are the kinds of things that we're going to be looking at today. Okay, so remember again, stars that are really massive, above 10 times the mass of our Sun, will end their lives catastrophically in a massive explosion that can be seen for many, many millions, if not billions of light years away, as they outshine their entire galaxy when they explode. And when they explode, they create all of the abundant elements in the universe. Anything bigger, more massive, meaning any element on the periodic table greater than iron, which is Fe on this thing. Fe is 26. Look at the 4th row right in the middle. Iron is Fe. And that's the heaviest, most bound element in the entire periodic table. But everything larger, below iron and to the right of iron and down from iron and higher atomic number than iron, was made in some sort of supernova. So these top 10 elements, in terms of their most abundant, it's hydrogen, helium, oxygen, carbon, all the way down. Notice they're all less massive than iron. But all the important things for life, like carbon and oxygen and nitrogen and iron itself, hydrogen do because of water and acids and bases and all sorts of things that hydrogen provides, that's where they come from. So nucleosynthesis occurs in the largest stars. They all fuse hydrogen into helium as part of their main sequence lifetime. But when stars are much, much older or much, much bigger than the Sun, 8 times the mass of the Sun, they will convert light elements all the way up to iron and nickel, and then those accumulate in layers, and then there's an explosive fusion that happens that builds even more light elements up to iron and nickel, but that also sets up a huge number of reactions that inside of the explosion, where the densities are extraordinarily high inside the core of the star as it's exploding, that create huge numbers of very heavy elements all the way up to, say, californium, which is 254 atomic nucleons in its protons and neutrons inside of its nucleus. So these things get all created, the vast majority of which are radioactive and then decay back down all the way down to iron. So the more massive things decay back down to iron or find a stable nucleus that doesn't decay. And then we find that supernova explosions are literally responsible for creating every one of the heavy elements seen in nature, except for hydrogen and helium, which were formed in the Big Bang. So supernova remnants, these things are the exploded elements of the star, because most of the star gets blown apart when it explodes, when these massive stars explode. So of a 10 solar mass type star or a 20 solar mass type star, perhaps 10, if it's a 20 solar mass star, perhaps at least 10 solar masses gets exploded out into the cosmos as a result of the explosion, where some of it may fall back down to a neutron star or a black hole, but some of it was ejected as part of the latter portions of the star's life and forms a nebula around it. And if there is a nebula around it, then the supernova's light can slam into that nebula and illuminate it, like we saw with supernova 1987A. And the blast wave then can plow into the interstellar gas, which is partly created by the supernova itself. And then it stirs and heats up the medium, and it makes it hot enough. And this kind of nebula lasts a couple thousand years after the explosion. So this leads us to the concept of stardust. The metal enriched, and by metals we mean any element heavier than helium. That's what astronomers call metals. Metal enriched supernova it mixes with the interstellar gas that creates new stars, that becomes part of the new star mix, because stars are almost all hydrogen and helium. Remember, the oldest stars have very little of elements heavier than hydrogen and helium, but the very youngest stars, meaning stars formed within the last 5 to 10 billion years, do not have or have a significant enrichment of, say, carbon, nitrogen, oxygen, iron in their atmospheres because of the previous stars out of dust out of which they formed. And that's where the silicon and oxygen and carbon and everything that we know of that makes up the entire planet Earth was formed. It was formed inside of a star that exploded maybe 5 to 10 billion years ago. And the material then floated around the galaxy, floated on the Milky Way until it combined with another interstellar cloud. That interstellar cloud collapsed, as we saw, just like the interstellar medium and star formation in previous lectures, that it collapses down and forms other stars. So the solar system was formed from a gas enriched by previous generations of massive stars. And that's where all the planets come from. And therefore, star formation is cyclical. They form, they evolve, they die. And they make more heavy elements that then go out into the interstellar medium. And what this does is it actually takes away some of the hydrogen in the galaxy. And so much of the hydrogen can be used up. If there's not a lot of hydrogen gas, then you can't have star formation. You need to have a big cloud of hydrogen gas. And eventually, that will all be used up, and there'll be just stars or just dust. And if you just have dust and just have stars, you can't form new stars. And we'll see in the galaxy section that there are certain types of galaxies, like ellipticals, that don't have any star formation going on. So they have very, very, very low metal type stars. Anyway, that's where stars come from. That's where so today what we're going to talk about are some historical supernovae that actually light up the skies today. In 1054, there was a guest star in the constellation of Taurus. It was seen by Chinese astronomers way back in 1054, and it was visible during the day for about a month and visible at night for almost 2 years. I think I got the wrong number here, 6 months. No, actually it's closer to 2 years. And this thing left behind the Crab Nebula, or Messier object number 1. And in 1572 and 1604, 2 supernovae occurred. The one in 1572 was written up extensively by Tycho Brahe. In 1604, Johannes Kepler wrote extensively about the supernova he observed. Now, they weren't the only people who did the observations. It's just they're the people who wrote the most about it, so we basically named the supernova after them. But there were numerous people who were watching the skies at that time, and they all saw this happen. So it wasn't just like some guy saw it. No, everyone on Earth saw it because they were bright enough. They were incredibly important supernovae, and they influenced astronomy and modern culture of their era. This is pretty important to remember how devastating these things could actually be for culture on Earth. And finally, we'll also talk about a supernova that happened between, say, 6,000 and 8,000 BC, the Vela supernova, and it was observed by the ancient Sumerians, and it appears in some of their ancient legends. So first, let's look at the Crab Nebula. The Crab Nebula is very, very prominent in the sky, and the Crab Nebula itself is something as by Messier object number 1, the first in Charles Messier's catalog of the 1700s. He actually went outside and looked at it and found this fuzzy patch in the sky and said, "Oh, that's not a comet, so I'll make it my list of things don't bother looking at because it's not a comet." However, back in July 4th of 1054, Chinese astronomers saw this new star in the sky, and it was much brighter than Venus, and it was visible during the day for about 2 years, and even it was seen by numerous cultures across the world. And if you look, we see this interesting petroglyph in Chaco Canyon, which is in the Four Corners region of New Mexico. And you can actually hike up and go see it. This area is, of course, kind of walled off because nobody wants to go mess with it. And there's a big old wasp nest up there. You can take that picture. I'm sure somebody will go knock that down because who wants wasps, right? Around you while you're trying to look at these pretty things. But you see there's a star-like image, a moon-like image, and a hand. And this is really interesting because the Anasazi actually gave us a map of where to look on that date for that new star. Because if you use a planetarium software such as Stellarium, you can actually go and go back in time to, say, July 4th, 1054, and you find just at the morning sky, the moon was right next to the Crab Nebula, and it was a crescent moon. And the crescent moon itself was right above the Crab Nebula, and the moon, and then the sun rose rather rapidly after this. Was in the morning sky, but then it's interesting is that the Anasazi had to have seen this arrangement in the sky, because the next day the moon is 15 degrees away. And when it comes around again next month, it's actually in a completely different place in the sky. So they actually saw it on July 4th, 1054. They saw it in this position in the early sky. And the moon, when it gets back to this place in the sky, does not have the same phase, and it does not have the same location. And in fact, the sun and moon have slightly different positions, and makes it harder to see. So the Crab Nebula was visible, and the other thing that's interesting is look over there on the upper right, we see the head of Taurus the Bull with Aldebaran and the Hyades over there, which is that star cluster that we talked about extensively in the previous lectures. But then if you carefully go back and look at the image from the Anasazi, you see this new star, you see the crescent moon, and you see the hand. Well, the hand has 5 fingers, and if you look at the V shape of Taurus with Aldebaran, those are 5 bright stars. So the V shape can be looked at as the 5 fingers. So we could think of them as the 5 fingers, the moon, and the star. And so the Anasazi were telling us that they saw this thing on that morning as the star rose. It was much, much, much brighter than anything else in the sky, and it was right next to the moon in the sky, and they could just see the fading glow of the Hyades in the sky along with it. And they found this to be so significant that they actually drew a picture of it and permanently drew the picture on the rocks so it could not be forgotten. And that's what they did back in July 5th. Of 1054, or July 4th, the morning of July 4th in 1054 AD. Well, that exploded back then, and here's some vital stats about Messier object number 1 to Crab Nebula. The mass of the progenitor star was about 9 times the mass of the Sun. The amount of ejecta inside the nebula that you see in the inset was about 2.5 times the mass of the Sun, which is an enormous amount of material. And there's a central neutron star, which we'll get to in the next set of lectures. And the central neutron star is about 1.4 times the mass of the Sun. The distance to the Crab Nebula is over 6,000 light years. So to have something so bright that it outshines Venus and can be visible during the day, 6,000 light years away, almost 6,500 light years away, meant it was extraordinarily bright in the sky. And if you go taking a peek at it, the angular size is about 5 arc minutes by about 7 arc minutes. And remember, there are 60 arc minutes in a degree, so it's actually a rather sizable nebula in a small telescope. I have hunted for it repeatedly, and I've always found it to be a very unsatisfying nebula. So you should if you want to go see it, you got to go see it, try to get it photographically, or what you want to try to do is use a very large aperture scope of at least 15 inches or greater in order to see it. The radius of it depends on which angle you're looking at. It's about 4 light years across one way and 6 light years across the long way. And the speed with which the material that you see in inset is going is up to 1,500 kilometers per second. So that's really cooking by. The total luminosity is much, much, much greater than the Sun's at about 1.38 times 10 to the 34th watts. And the total amount of energy that's coming out in X-rays is just under 10% of that. Now, most of the luminosity, a significant fraction of luminosity, comes out in radio light, and that's in fact, this is a significant fraction of the total luminosity is in radio frequencies. What you're also looking at, the nebula itself, is permeated by a very strong magnetic field that is much, much stronger than the Earth's magnetic field, and the formation in order to create the nebula itself, or create the formation of this thing. What energy did it take in order to make the neutron star that's powering the appearance of the nebula? cost an enormous amount of energy, much more energy than the sun will put out in its entire lifetime. In fact, that's more energy than a billion stars will put out in 1 second. So there's this pulsar that's emitting radio pulses in the center that goes every 300ths of a second. So that's faster than you can snap your fingers. Something is blipping out there, and that blipping is slowing down by about 100,000th of a second per year. And that's called a pulsar. And we'll talk about pulsars and neutron stars next time, but I just wanted to show you that. So the Crab Nebula has many observational characteristics, and so we see the Hubble Space Telescope image taken with the Wide Field Planetary Camera 2, and this was taken by Hester at Arizona State University with the Hubble Space Telescope. And we see that the Hubble can see it's a narrow band filter set, and we can see that it looks like an astonishing wreck. And the changes are actually easily seen by going back and looking at the Crab Nebula over time. Now, why it's called the Crab Nebula, it's kind of weird. It doesn't look much like a crab to me. But when the Earl of Rosse looked at this with his Leviathan telescope, which we'll talk about when we talk about the Great Debate of the 1900s, about the distance to the spiral nebulae, Earl of Rosse looked at it, he sketched it, and he sketched a crab. I guess that's what he saw in a telescope visually. So, before photography, people made sketches, and that's his sketch was of a crab. So that's what he called it, and the name stuck because the crab. Why not? So we see other images on either side. The upper left is X-ray emission at various frequencies. On the right is high-energy X-ray emission from the central region, and we see some bright dot with some disk-like structure and some sort of jet. We also see the superimposition of the X-ray image on the upper right, superimposed on the Hubble Space Telescope and in Spitzer Space Telescope image in the lower right. And we can see that the X-ray luminosity comes from a sizable portion of the image in the center. And then if you take an image and put a polarimeter inside it and look at sub-millimeter wavelength, which is much longer than infrared, and that's what you get in the lower left. And you get a polarized image of it, and the polarimetry gives you the fact that there's a strong magnetic field. So let's look first at the polarized image. This was taken with a large apex bolometer camera at 870 microns. Remember that the typical wavelength of light is this is just under a millimeter in wavelength, but wavelengths of light are 10 to the minus 7th wavelengths, are 1,000 angstroms, or approximately 10 to the minus 7th meters, or a tenth of a micron. So this is about 1,000 times the wavelength of visible light, and that's the blue, red, and yellow that you see in this. But the lines indicate the polarization of the light. And so how you get the polarization is you put a polarizing filter, which we talked about in one of the earlier lectures, and a polarizing filter is basically a bunch of slats. And these slats go in front that only allow light whose electric field is vibrating in a particular direction to come through. And then you look at exactly where it is brightest, and that shows you the orientation of the polarization. And the Crab Nebula is strongly polarized, which indicates that it is a strong magnetic field, which is shaping the emitting electrons' orientations. So something is making it polarized. And this was given at a proceedings of the SPIE in September 12, 2012 with the introduction of this camera. Well, the explanation for all of the light that's coming from the Crab Nebula comes from synchrotron emission. So what is synchrotron emission? Well, if you take a very strong magnetic field and you accelerate electrons somehow up to nearly the speed of light, they will spiral around the magnetic field lines and travel along these helical paths at nearly the speed of light and spin and spin and spin. And as they go around in these helical paths, because they're accelerating, moving in a circle, but then that circle is getting dragged along upwards, as they're circling in the magnetic fields, that's an acceleration because a circular motion implies an acceleration towards the center of the circular motion. that means they will emit light, and they emit light in a specific way, and that specific way is given in the graph on the lower right. So a single electron is given in the upper right of the lower right of that thing, and it shows what the emission is like for a single electron. Now, if you have billions upon billions, or 10 to the 37th electrons, or 10 to the 50th electrons, something like that, spiraling around magnetic fields, you add up all those individual contributions, and the slopes on the things that go down to the right show you what the sum of all the contributions are, and it makes like a flat power law. It makes a yellow dashed line where you can say, oh, this is the power law emission of synchrotron radiation, which means that the nebula is not hot. It's not hot in the sense that we think of hot, because this is non-thermal emission. And non-thermal emission means it doesn't all have the same temperature. Now, if you had this gas that's going, really, really fast at nearly the speed of light, and it's mostly composed of electrons, you'd get hurt and it would give a sting of burn. But when we think of things that are hot, we think of things that all are at the same temperature, and all have this, and that temperature characterizes the average motions of the randomness of the gas or solid that you think of. So on a hot day and a summer night, the air is hot because it has been warmed by the sun, so all the molecules in the atmosphere get warmed, and so as they get warm, they all move fast on average. But when you look at synchrotron emission, there's nothing for the electrons to bump into. So since, unlike the gas in the atmosphere when it gets on a hot day, the atoms and molecules in the Earth's atmosphere bump into each other and transfer energy until they all are moving roughly at the same average speed. Some are moving faster, some are moving slower, but the temperature can be roughly the same. And that's why we call how hot is it out. But the electrons in this magnetic field don't bump into each other. They simply spiral around the magnetic fields and emit light. And this emission of light is called synchrotron emission, radiation. And it's not thermal. It's not a thermal process because they're not bumping into each other. Now, they're moving fast, but they're not bumping into each other and interacting to average out the speeds. And the electrons themselves are moving so incredibly fast. They're moving much faster than can be done in any particle collider on Earth by hundreds of times. So something's driving the energy of the electrons inside the Crab Nebula up to energies that are much greater than we can do in the Large Hadron Collider. And so here's another view of what we mean by that, of the electrons spiraling in a magnetic field, and as they do so, they emit light. And on the left-hand side, what we do is we see two types of emission, and see that bulby sort of thing that looks like an onion. Now, if the electron is moving slowly inside the magnetic field, it's accelerating towards the center in a circular orbit as it orbits inside a magnetic field. And if it's moving slowly, then the electron emits in all directions, and the light is not polarized. But if it's moving very, very, very fast, nearly the speed of light, then it actually gets narrowed and polarized into a beam, because that bulb now that's shooting out to the side, that's the shape of the emission of the electron as it spirals around. It doesn't take the emitting in all directions. In the electron's frame of reference, it is. But to an observer away from the electron, it does not. It looks like it's going in these beams. And that is an effect of general relativity, or special relativity more specifically. So as you spin an electron faster and faster and faster, it gets the light that it emits from synchrotron emission gets beamed and polarized. And it gets polarized along the edge of the circle that is being polarized along. So we can see that this is a bulb sort of shape, and it's also a flat, tall bulb. And the flat, tall bulb is the orientation of the polarization. So the Crab Nebula emits enormous amounts of X-rays, and these X-rays are also emitted through the synchrotron process, and we can see pretty easily inside this thing that there's these strange filaments and like bay-like structures and loops and curls, and what we're seeing here is something that's approximately a couple light years across, and right in the center is the thing that seems to be driving it. There is some sort of disk of material that seems to be spreading outwards from it, and there's like a jet sort of puffy thing coming out from the center, and that thing that's in the center is called a neutron star, or a pulsar, because it does pulse in a certain way, not in and out, but rotationally it pulses. There's a pulse associated with its rotation. but it's rotating very, very, very fast, about 33 times a second. And it's a very tiny object, and we're going to discuss what those kind of things are later. But the energy of this object and the density of this object and the provides all of the electromagnetic energy to fuel the electrons to spiral in the magnetic field such that they can spiral around in that noodly looking magnetic field structure and emit X-rays via synchrotron radiation. And if we look closely at this, we've now overlaid the X-ray image in purple on top of the Spitzer image, which is in red, and the yellow, which is the Hubble image. And remember, it's about 4 light years wide and about 6 light years long. So the X-ray image is emitted from an area that's about 2 light years across on either side. So that jet, that plumy jet in X-rays, is about a light year long. That's coming from the center, which is that bright dot in the center, and that is the pulsar neutron star that is causing all of this damage. And there's a close-up of it, and we can see that there's a bright dot. Don't worry about the bluish bright dot right above the central bright dot. That's a foreground star. But what we see is that there is there's a disk-like structure, and this has been shown to be moving and rotating, and we'll talk about more about that when we talk about neutron stars next time. So synchrotron radiation, though, is and the reason we think that this is the case is that the emission that's happening is so incredibly vast from these things that the X-ray emission would be so great that it would actually lose its energy because it's spiraling out, it's emitting energy, so it doesn't do this forever. So it loses its speed as it's moving, and therefore spirals down, and so the electron then, instead of emitting X-rays after a few, like 5 or so years, it then slows down until it's emitting light only in radio frequencies. And when it's emitting in radio frequencies, it'll take about 1,000 years for it to slow down where it's not doing that either. So synchrotron radiation spans from X-ray to optical light to radio light. And that's why the Crab Nebula has incredible amounts of radio emission, because there's still a ton of electrons spinning around that are being replenished by this pulsar that's at the center. Now another bright supernova is the one that was observed in 1572. There were a couple of really important cultural things that happened around this time, and in between November 2 and 6 in 1572, there was a bright star in the northern sky in the constellation of Cassiopeia, and in fact you can see it in this image. I'm going to use my mouse to pass over the Cassiopeia. We see the W of Cassiopeia, and we see the bright star below it. Now Tycho Brahe made his name on this. He was really good at actually being a publicity hound, and he wrote extensively about this in his book De Nova de Nullis Aviae Mormaria Prius Visa Stella, meaning the new star. And he published it 3 times, once in 1573, again in 1602, and finally a 3rd time in 1610. And it contains all his observations and the analysis of some other observers, including some of his competitors who he disrespected and threw some shade on, which was really kind of cool. But when it first emitted its light, it was brighter than Venus, and in fact, it was even used as the opening line in Act 1, Scene 1 of the play Hamlet. And so if you go take a look at it, remember the play Hamlet is actually called a disaster. Not just the tragedy of Hamlet, but is the disaster of Hamlet, meaning bad star. So disaster, meaning bad star, was actually part of the vernacular and part of the thinking of both the mythological and superstitious thinking, said that if you were born under a bad star, and you can even think of Romeo and Juliet as being star-crossed lovers. So with these disasters, and if you have a disaster, you would write about it, and that's what Shakespeare did. Funny enough, there's also references to Tycho Brahe's subsequent difficulties with the King of Denmark, because that's where he lived. And on the island of Uraniborg had some other names as well, such as it was pretty close to the island of Elsinore. And in fact, Tycho Brahe had 2 kinsmen. One of them was named Rosencrantz, and the other was named Guildenstern. So those 2 characters appear prominently in Hamlet as well. So there's a very strong link between this supernova, Tycho Brahe, and the play Hamlet by William Shakespeare. And this is the observation that Tycho Brahe did in 1572, and we can see the star marked by the letter I as being the new star, or Nova Stella in Latin. And we see the W of Cassiopeia that he drew out in the stars G, C, D, E, and F that make out the W of Cassiopeia. And it was bright enough to be seen for a very, very long time. And we call this supernova 1572A because it's the first supernova of 1572 that's recorded. And on the lower right, what we're seeing is an X-ray image taken by the Chandra X-ray Observatory after it was launched by the Hubble Space Space Shuttle. And if we then go look in the infrared with the WISE observatory, which is the Wide Infrared Survey Explorer, Wide Field Infrared Survey Explorer by NASA Jet Propulsion Laboratory, Tycho's supernova shows up really bright in infrared as a spherical distribution. And that's because as the material from the supernova plows into the interstellar medium, it warms the gas and dust around it. And there's a bunch of gas and dust that you can see from the nebulosity that surrounds it. And it's heating that gas as the supernova material plows into it and warms it up enough to see. So Tycho's supernova also has some very interesting appearances. It's got this mottled sort of appearance, and it's brightly emitting in X-rays. And there's actually some different wavelengths of X-rays that are shown in these colors because of the different colors. The starry background is of course not X-rays. That is a digital sky survey that was just put as a background image just to show you what it looks like in the sky, if we could see it. But the foreground is the supernova remnant itself from 1572, and it was actually visible until about 1574. So it stayed visible in the sky for just about almost 2 years. Then in 1604, Johannes Kepler saw a star in the sky that was even brighter. And he wrote a bunch of things, and his book was called De Stella Nova Indepedia Serpentari, which is the star in the serpent bearers, which is Ophiuchus, the Ophiuchus, the serpent bearer constellation. And those two stars that erupted forth in 1572 and 1604 assisted Galileo and Kepler and Brahe and many others in saying that Aristotle's ideas of the cosmos, that the heavens are unchanging and immutable, was wrong. And that was a philosophical change, because if the stars could change, then perhaps the Earth could move around the sun. And that was the big, big, big argument of the day. Does the Earth move around the sun? Copernicus said as much, but only published after his death. Galileo went into house arrest because he asserted that, and Kepler was just simply wandering around Europe trying to do the mathematics of it and trying to understand how it actually worked. Went over to Tycho Brahe, who Tycho Brahe himself didn't think that the Earth went around the sun, but he kind of made something modified. But Kepler eventually took the idea of the unchanging heavens being gone and replaced it with the Earth going around the sun, which then subsequently came back to Newton. Well, subsequent to that, the Hubble Space Telescope did a good observation of Kepler's supernova 1604A, and this is the view with the advanced camera for surveys that was done in August 2003, and we see the Hubble took a bunch of images in various narrowband filters that allowed it to look at specifically the light emitted by hydrogen, nitrogen, and oxygen, these specific things, and that's what you'd look for in a nebula such as this, because it won't be a thermal nebula, so you don't use a wideband filter, use a very, very narrowband filter and look for bright emission. And hydrogen should be expected from a type 2 type supernova, which has exploded outer rim of a star, and nitrogen and oxygen should also be there, and that's what's seen. So the whiteness comes as a mix of hydrogen, nitrogen, and oxygen as it plows into the interstellar medium. The red is, of course, the hydrogen that we know from old, and then the rest is starlight in the background. And so the puffy, cloudy nature is the supernova remnant from that time. However, that's not the only view. The Chandra X-ray Observatory and the Spitzer Infrared Observatory also take a look at it, and it looks completely different in those views. In the blue is the Chandra X-ray high energy X-rays, and those things come because as the material from the supernova, which is traveling at thousands of kilometers per second, slams into the interstellar medium, it heats the interstellar medium and makes it glow in X-rays, and that's what that blue glow is on the outside. As the material shock heats the interstellar medium into glowing to X-rays. So basically, you've got some cloud of gas and of hydrogen gas sitting around going herp derp. Not what I'm going to do. I'm some molecules, and all of a sudden something comes along and hits you going 10,000 kilometers per second. You're going to be angry and emit some X-rays too. So behind that shock front is a cooler X-ray emitting gas. That is the thicker interior shell. That is the heated material it's behind the shock front that is occurring from the supernova. And finally, we see in the upper right of this image the optical image of Hubble Space Telescope, which actually traces the upper right area of the supernova remnant, as well as the Spitzer infrared image, which mirrors kind of the low energy X-rays. And that comes from the fact that we have the cooler interior material that is the slamming into as the interstellar medium itself. Some of the dust doesn't get as it cools, as it is also warmed by the X-rays, and as it's warmed by the X-rays, it glows in infrared. So that's some of the remnant dust that survived, that then glows that glows because of the brightness of the X-ray emitting material that's coming through it. So let's take a look close up of the three regions. There's one region in the upper right of the remnant. And we can see in X-rays it's glowing brightly, and in the visible light it's glowing brightly, and in the Spitzer infrared telescope area it's also glowing brightly. And that's because as the shock front interacts with the interstellar medium, and that's must be a place where there's a particularly large interstellar cloud. And we talked about the interstellar medium as having cloudy structures, and they might be dark clouds out there, and this is just the supernova remnant slamming into one of those dark clouds and heating it up until it glows in X-rays, and then those X-rays then illuminate some of the dust, and that dust glows in infrared. And those X-rays also then cool off some of the things and make the gas, the hydrogen gas that's inside of the gas cloud, glow. So it illuminates this little poor hydrogen cloud of gas and dust that's now getting whacked and heated to X-ray emitting temperatures. Now what's funny is you can actually use this to actually determine the distance and the speeds. So what a number of researchers have done is actually have taken the Hubble Space Telescope, actually taken repeated images of the Hubble over periods of time, and looked to see what's moved. And when you see what's moved, then you can determine how fast it's been moving, and that's how they determine the speed, the velocity speed, by taking subsequent images and differencing them, and you can see how fast it's moving. So the bright shocks are not moving as fast as the really faint shocks. So the faint shocks are the ones that are plowing out straight out from the star, but the brighter radiative shocks happen as those faint, really high-speed shocks keep moving along as they have gone through the cloud, and then the others just glow because, well, they've been kicked. But in the same sense that, imagine you have something going really fast, and it's a small, say, car, and you hit a big car with a small car, the big car is going to move a bit, but the small car is going to keep on moving if it's small enough, and the big car might just keep on going. But it's more like maybe you have 1,000 little cars and one big car, and sure, a few of them are going to hit the big car, and as a line of them go by, but the debris will heat up and make an explosion, and the other ones will keep going on by. So it'd be kind of like a grand chase across the desert with a line of cars. I don't even know what I'm talking about with that. But anyway, there's a shock wave that occurs because the gas from the explosion, the initial explosion, moving about 2,000 kilometers per second, that then slams and heats into and starts into motion the interstellar medium at about 100 kilometers per second. And it's found by just looking at the difference in brightness between the three filters of hydrogen, sulfur, and oxygen, that there is a significant overabundance of nitrogen in this supernova, which leads to understanding that it's a type 2 supernova. And then we can look at, that's how it's also, the distance can be found. And here's how the distance is found. We take two consecutive images, spaced almost 20 years apart, and you can see that the actual shock wave has changed with time. So the green is from 2003 and the red is from 1987. And actually a ground-based image, and then that 1987 image was compared against the Hubble 2003 image, and it showed a proper motion of about 1.5 arc seconds in about 16 years. When you know, and that is assuming a radial velocity perpendicular to assuming a radial velocity across the sky, that gives you that makes like a base of a triangle, and that gives you the speed, first of all, of 1,600 kilometers per second at a distance of over 12,000 light years. So you can actually determine the distance by the proper motion of these objects as they cruise across the sky. And it's Synchrotron that gave this particular one, that image right that we see here. Next we have the Cygnus loop, which is an amazing, amazing thing to go check out in a telescope. Many of the features that you see here, and yes, the loop itself is much, much larger than the full moon, so you can't actually see it, the whole thing, in an individual telescope. The Cygnus loop, which is an enormous shock front, is moving at about 300 kilometers per second, over 1 million miles an hour. It's over 5,000 years old. It's over about 100 light years across. And if we think what was happening about 5,000 years ago, that was when the first civilizations were appearing. And so this is in Cygnus, which is a northern hemisphere bright star. So over 5,000 years ago, the first empires were built, the first cities were being built, the first Greek civilizations were being built, and there was an eruption of civilization at the time as this new star was gracing the skies above these people. And there's some beautiful pieces of elements of this thing, which is one of the wisps inside it called Pickering's or Fleming's wisp. And then there's the western veil, which sometimes is called the witch's broom, because the witch, which is that star, is riding the broom. And if we then look deeply with the Hubble Space Telescope into one of the elements of the witch's broom, we can definitely see that this looks like a shocked, heated region with these wispy, wispy things moving quickly across the sky. And as they move, this is visible light now, not X-ray light. But the visible light image, as the shock wave interacts with the interstellar medium, it heats it to X-ray degrees, and then that cools off and glows in visible light. And you can definitely see that this is mixing with the interstellar medium, and this is the process by which the materials in the star go out into the interstellar medium, merge with it, become part of it, and then initiate and then help to form more things, or actually seed new stars with the materials that could become planets. In this image alone, there's probably more hydrogen, more carbon and oxygen than there is in all the Earth, which is an astonishing thought to think, that that's how much material is in just these wispy-looking clouds. Next, we can say how far the Cygnus loop is, because with the Hubble Space Telescope image from the Wide Field Planetary Camera 2 that we see in the back, this can be viewed over a couple of different observations by looking in that upper area where it's very, very thin, where you can actually see the shock wave move over time, and then looking at how fast the width of the line, the width of the emission line in the upper left, shows you how fast it's moving. So the spectrum width shows the speed that the shock is moving. And so now you know that it's moving 170 kilometers per second. And then what you do is you go back and see what the angular motion is across the sky over years, and that tells you how long it took to get from where it is to go to the center. And that shows you how big this thing is and how old it is. And again, that allows you to find the distance to it. Now, you can see in these two images that there's the Wide Field Planetary Camera image of distance of only a difference of only 4 years is able to actually discern a change in position of these wisps. And with that proper motion change of the wisps across the sky and the speed derived from the width of the bright line inside of that, we then see that the distance is about 1,800 light years. That would have been really close to have a supernova 1,800 light years away. It would have been extraordinarily bright in the sky 5,000 years ago. It would not have been missed at all by anyone. Why are there so many religiously based civilizations that appeared 5,000 years ago? Did somebody look up in the sky and say, this was the most important thing. I know why this star is doing this. Follow me. Is that possible? Maybe the stars in the sky help us to change human culture. If we then look at Cas A, which was possibly came about in the middle of the 1600s, it was a 30 solar mass star that exploded, and it has X-ray emission as well, and it is powered by a neutron star. And we find from Hubble imagery that it is extremely bright, a oxygen emission, so it has an extraordinarily oxygen-rich supernova remnant, as well as another supernova remnant N94, which is again part of the Large Magellanic Cloud, and so it's very tough to see from the ground. In fact, you can't. So this is a really tricky one from Hubble Space Telescope data, and that's a very distant object in the Large Magellanic Cloud, about 1,600 light years away. Here's another supernova remnant that spans about 70 light years across, and it's only about 5,000 light years away, and it's between two very bright stars, Eta and Mu Geminorum, which are bright stars in the constellation of Gemini, and it's a rather big object. The size scale that we're looking at is that this thing is about 50 arc minutes across, which means that it's actually that bubble, that red bubbly shape, is actually twice the size of the moon in the sky. But it's hard to see in the sky without photographic telescopes. In fact, it is not possible to see without photography. And the reason it's bright in the upper left-hand area of the bubble is because it's slamming into that emission region in the upper left, in the behind the words in this image. And so as it slams into that hydrogen gas, it makes it glow, and it emits X-rays, and that then emits visible light in the form of hydrogen gas emission. There's another one, Supernova Remnant 132d, and possibly a supernova that will occur in our lifetimes, which is Eta Carina, which is in the southern hemisphere. But if it goes off, we'll definitely be able to notice that, but only people in the southern hemisphere, not northern hemisphere. And the Hubble Space Telescope has been looking at it. We see observational emissions of the thing shredding itself with ionized iron and nickel, argon and helium all throughout its spectrum. Now, all of these massive stars, these supernova massive stars, can be iron-rich supernova, and that's how we know that the oxygen is actually permeating the cosmos. By knowing their distances and their expansion rates, we can compare their relative sizes. Cas A is only about 350 years old. There's another one that's 2,000 years old, and N132d is about 3,000 years old. And all of these things are just expanding and expanding, and as they do so, they enrich the interstellar medium. And if you go out and look at other galaxies, such as M83, M83 is just creating supernovae like crazy. It's about 15 million light years away, and the smallest feature on the inset is about 72 light years. This is a barred spiral galaxy, has a starburst nucleus, and there's been 6 supernovae since 1923 that have been observed in it by astronomers. And there's huge numbers of core collapse stars in it, and at least 200 supernovas in less than 3,000 years have happened in this galaxy, only 15 million light years away. So if we zoom in on a particular thing, how do you look at this thing and determine what the supernova remnants are? Well, you look at their spectra. And the spectrum of an M83 supernova, we have 4 different lines that are actually highlighted by these different red items. And hydrogen emission is roughly the same between that and, say, an H2 region on the bottom. But a supernova remnant has oxygen emission. And so strong oxygen emission with strong hydrogen emission, and even strong sulfur emission, which is the blue line, S2, and O3 is the oxygen emission in green, that tells us that it's a supernova remnant as opposed to an emission nebula such as the Orion Nebula or something. So then you go and look for these circular sort of regions that are emitting a lot of oxygen, and this is what you find. You just go in front of these bulbs, and boom, 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 people are going and hunting and going and finding them and looking and looking and looking. And in fact, this group found 60 supernova remnants inside just that image that we were looking at before. So if you actually reduce that down, that image, and play with it, you can actually find these objects all throughout this other galaxy, and they're everywhere inside there. These supernovae have been popping off all over the place. And if we then just look at the core region alone, you can see there's like 24 of them right in the core of the starburst core of that galaxy. But now I'm going to finish on one of the more interesting supernova remnants that possibly helped start civilization, or at least what we would call agriculture. And I'm going to make this assertion, and I know I'm wrong, but I'm just going to go with it. The Vela supernova remnant, about 11,000 years ago, in the southern constellation of Vela, there was a star that exploded. And when it did so 11,000 years ago, the outer layers of that star crashed into interstellar medium, making the shockwave, and that's what that fluffy shockwavy sort of puffy thing is in the center of this whole thing, by a sky factory, which was processed by David Martin. And so this image is also visible in X-rays, and this whole puffy, cloudy sort of, that's the wispy sort of webby thing that's in the middle. That's the nebula, that's the supernova remnant. The rest of it is H2 regions and star-forming regions, but the webbiness is from the exploding star that happened about 11,000 years ago. And there's a view of it in H-alpha taken by the Anglo-Australian Observatory. But the reason I bring this up is because Göbekli Tepe is an archaeological site found in southeastern Turkey. And it's known that this thing, now the actual age of the Vela supernova remnant is not well established. However, the tell, and the tell is just the dig itself. And there are two phases of ritual use in this that date between roughly around 9,000 BC. And that's between 10 and the site was created. Lots of pillars were erected in a very regular structure, and each of these pillars in this regular structure has no administrative significance. It's on the top of a hill, and there's no living quarters amongst this thing. But this is the earliest part of the Neolithic period of human history. This one particular archaeological site from 9,000 BC is the earliest human structures built in the world. And this marks the beginning of the Neolithic era of human history. And they put a bunch of stones on top of stones. And the German archaeological team dug there for almost 20 years under Klaus Schmidt. And Klaus Schmidt has an amazing TED Talk about this thing. And he tells about the efforts to uncover it and how important it is. And only weeks after he gave the TED Talk, he passed away. But through his incredible efforts, this archaeological treasure was unearthed in Turkey, and the Turkish government immediately gave him permission to do so, because if you find an amazing archaeological site in the home country of and know that this is one of the most ancient sites in all of humanity, it's fascinating to think that this happened at about 9,000 years ago, or 9,000 BCE, which is about 11,000 years ago. The Vela supernova remnant is about 11,000 years old. Perhaps the stone structures that are in a circle that we see here are actually in arrangement to describe this cosmos. The circular arrangements, the oval shapes, are maybe in honor of all of the shapes of the stars in the sky. Now, many of the pillars in these structures, and they have these T-like structures, which are not seen in any other archaeological tell in the entire world. And when this died out, this culture in Göbekli Tepe died out only very soon after its foundation. Nothing like this happened again for approximately 4,000 years. And that's when the next supernova went off. It's interesting how this worked. And all of these stones have inscriptions of like animals that were familiar to the time. Well, what do we do when we look up in the sky? We see Taurus the bull, Aries the ram, Lyra the lyre. There's Cygnus the swan. We have the serpent bearer. We have the lady in the chair. We have all, and Scorpius and Cancer the crab. We name so many of the objects in the sky after animals on the ground or mythological beings. So it makes sense that if some great, great, great star appeared out of nowhere, you'd want to honor it. Or maybe somebody said, I know why that star is so important, and so convinced everybody to actually build these structures. Because in Klaus Schmidt's video, they actually tried to reconstruct exactly what it would take to build some of these things. And it takes hundreds of people just to put these stones on top of other stones using Neolithic technology, such as sand and ropes and wood and other stones. So this was a major undertaking that required major commitment and major enforcement of that commitment. Because most people at this time, they were agricultural, or shepherds, and they went from hunter-gatherer societies to agricultural societies. But what exactly inspired these people to build this? Klaus Schmidt really doesn't know, but it's telling and very fascinating to think that we named the animals in the sky after animals we know. And all of these stones are set in circles, which are familiar from our studies of geocentric concepts about the cosmos. And the stones might very well be things that mark the constellations of that they know. But there's no necessary, but I'm sure that Klaus Schmidt would vociferously argue at this point, and there's nothing direct in the archaeological record, I'm sure, that deliberately says, oh, they're looking at a star in the sky. However, this occurred, and then 5,000 years later, another one occurred. And these stars, and when 1572 and 1604 came around, and those stars occurred, that changed much of human history. And so that we can also remember that the Reformation of the Catholic Church, or at least the Protestant Reformation by Martin Luther at the time, happened right around the time of the two supernovae. And this was the time when Martin Luther was saying that you don't need the hierarchy of the church in order to talk directly to God. So he hammered his note on the door right around the same time as these supernovae went off. So supernovae do a lot of things. If one were to go, and the last one that was seen naked eye was 1604 until 1987. That was the first one since 1604. So another one might go off at any time in our sky. There's no way to predict them. And when they do, it might cause a big change. It might cause somebody to, build a new religion. But at the very least, that star's explosion goes out into the cosmos, seeds the cosmos with more gas and more dust, enriched with iron, nitrogen, oxygen, and carbon, and all the elements of the periodic table, and those then merge to form other stars, which then make new planets. So we are looking at a wisp of gas, but that wisp of gas has more mass of carbon and oxygen in it than thousands upon thousands of Jupiters and Earths inside of that wispy-looking cloud. And that's what we really think about supernovae, that they are the beginnings of possibly even the solar system. The shockwave could have begun the solar system's collapse out of this cloud of gas and dust. And we know that these elements must have been created there, because that's the only place where they would be. All right, so next time we'll be talking about neutron stars, white dwarfs, and black holes. See you soon.